Hello guys, welcome to Engineers Academy. Do subscribe Engineers Academy if you are here for the first time. Now we are going to solve this problem which says that determine the normal force, shear force and bending moment at C of this cantilever beam. So we are given this beam and the distributed load at point A is 1200 Newton per meter, and we are asked to find the normal force, shear force and bending moment at this point C. So there is no need to find the reaction at point A since we are going to consider this BC section. We can either consider AC section for finding the normal force, shear force and bending moment, these three internal forces, or we can consider this BC section of this cantilever beam. So now if we are considering this BC segment, then there is no need to find the reactions at point A. And if someone is interested to consider this AC segment of the beam, then we need to find the support reaction at point A. So I'm going to consider this BC segment. There is no need to find the reactions at point A for my calculation. So now to consider this BC segment, first of all we need to find the load, the distribution load intensity at point C. So let's say that that load distribution at point C, the height of that load distribution is represented by WC, and to find that WC we need to consider two similar triangles. So one triangle is this and another triangle will be like this. So we will have two similar triangles which are shown here. So we have this large triangle and then we have this small triangle, and the large triangle, the base of the large triangle is 1.5 plus 1.5, that is 3 meters, and the base of the small triangle is 1.5 meters, since point C is at a distance of 1.5 meters from this end of the beam. So that is 1.5. Here we have that point C. So now to find this WC, which is the distributed load intensity at point C, we are going to consider the similar triangles. So we can consider the ratio of this 1200 Newton meter divided by this base. So the ratio of this divided by this will be equal to this WC divided by this. So the ratio, the ratios of the corresponding sides of a similar triangle are always equal. So we can say that WC divided by 1.5, this ratio must be equal to the ratio of 1200 divided by 3. So again I'm going to repeat that this WC divided by this 1200 Newton meter divided by this base. So this ratio will be equal. This is the property of similar triangles. So from this we can say that WC is 1200 divided by 3 multiplied by 1.5. So 1200 multiplied by 1.5 divided by 3, this gives me 600. So this will be 600 Newton per meter. So now we know this WC, this is 600 Newton per meter. Now to consider BC segment, we need to cut this cantilever beam. So let me cut this. So this will be our free body diagram, and then we need to consider the internal forces. So at C we will have the normal force. Let's say the normal force is going to act in this direction. This is NC, and the shear force is going to act in the upward direction, since in the previous video I have discussed that the positive convention towards the left of the section will be in the upward direction for the shear force. So this is VC. And now the bending moment at C is going to act in the clockwise direction. So this is our positive convention on the left hand side of the segment. So this is MC. BC, we are interested to find the normal force at C, the shear force at C, and the bending moment at C. So again, this BC segment is in equilibrium. We can always apply the equilibrium conditions. So the summation of forces along x, that must be equals to 0. Towards the right is our positive convention, so we will have minus nc, since this nc is only acting in the horizontal direction. So minus nc equals to 0, or we can say that nc is equal to 0. But before going to apply the equilibrium condition, we have to find we have to replace this distributed load by its resultant force and by its resultant concentrated load. And the resultant of this distributed load must be acting at the geometric center of this triangular shape, of this triangular geometry. So the geometric center of this triangular shape is at a distance of 1 divided by 3 of this base from this end, and 2 divided by 3 of the base from this particular end. So let's say that this particular point is at a distance of 1/3 of the base of this triangle. So 1/3 into this base, which is 1.5. So 1/3 into 1.5, 1/3 into 1.5 is 0.5. So this means that this geometric center is at a distance of 0.5 meters from this end, and from this end it is 2 divided by 3 times 1.5, 2 divided by 3 times the base of this triangle which we are considering for the distributed load. So from that end, that will be 2 divided by 3 multiplied by 1.5, that must be equals to 1 meters. If from this end, if this distance is 0.5, then from this end that must be 1 meters. So now we need to draw we need to replace the distributed load, the triangular distributed load, by its resultant, and that the line of action of that resultant must pass through this geometric center, which is at a distance of 0.5 meters from this end. And now this resultant will be equal to the area of this distributed triangular load. So now the area will be 1 divided by 2, the base of this triangle. So the base of this triangle is 1.5, so 1 divided by 2 multiplied by 1.5, and the height of this triangle. So the height of this triangle is 600 Newton meter. The height of this triangle is WC. So we will multiply this with 600 Newton meter. So this 1.5 is in meter, this 600 is in Newton meter. Meter will cancel, so the units of this resultant for that distributed load will be in newtons. So 2 into 1.5 into 600, it is 1 divided by 2 multiplied by 600 multiplied by 1.5, so that is 450. So we can write that that triangular distributed load from point B to C can be replaced by a resultant of 450 Newton concentrated load, and that concentrated load is acting somewhere here, and this distance of this concentrated load from point C is 0.5 meters. So now we can look into this diagram. I have explained everything. So this point, the point from where this resultant is passing is at a distance of 0.5 meters, and this 0.5 meters is 1/3 of this BC length, which is the base of the triangle. BC length is 1.5, so 1/3 of 1.5 is 0.5, and this resultant is equal to the area of this triangle, which is half into the base into the height. So half, base is 1.5 and the height is 600 Newton meter. Considering the segment BC, we can apply the summation of forces along x. The summation of forces along x gives us NC equals to 0. Now we can apply the summation of forces along y. The summation of forces along y, this must be equals to 0. In the upward direction is our positive direction. So we have Vc plus Vc minus 450. So plus Vc minus 450 equals to 0, and Vc is equal to 450 Newton. So the shear force at point C is equals to 450 Newton, and it is acting in the upward direction since we got positive 450 Newton. So the positive sign tells us that the assumed direction is the actual direction, that is the accurate direction. Similarly, we are going to consider the summation of moment about point C equals to 0, and the counterclockwise moment is considered to be positive. Now, as we can see that this Vc is passing to that point C, it's not going to produce the moment about point C, and C is 0. So, and this MC is a free vector, so we will write that this MC is in the clockwise direction, so we will write minus MC, and this 450 Newton is producing the clockwise moment as well, so we will write minus 450, and the moment arm of this 450 Newton force from that point C is 0.5, so we will multiply this 450 multiplied by 0.5, and this is equal to 0. 450 into 0.5, this is 225, so minus MC minus 225 equals to 0, and from this we can say that MC is minus 225 Newton meter. So the negative sign tells us that the assumed direction is not accurate. MC is, the bending moment is in the downward direction at point C. So MC magnitude is 225 Newton meter, and its actual direction at point C is in the counterclockwise direction. So the normal force at point C is 0. The shear force at point C is 450 in the upward direction, and the bending moment at point C is 225 Newton meter in the counterclockwise direction. So this is the solution of this particular problem. I hope it will help you in your learning. Do subscribe Engineers Academy if it helps in your learning.